Hi, welcome to the Dabble project. So let's just get right into it. First, I'm going to give a quick demonstration of the project. And the first thing that you'll notice is that it's very simple. When I spin the potentiometer, the value goes up on the serial monitor, and it's really just echoing what's reported by the ADC, which in a high-level language would be analog read. And at first glance, you might think that the program that's being run on this microcontroller is this program right here. We're just doing serial.begin, then we're constantly printing the value of analog read and waiting 500 milliseconds, hence the updates as I spin the potentiometer every 500 milliseconds or so. But in fact, this is not the program being run. This is the program being run, which is quite a bit more complicated and around 200 lines long. So the reason for this is that this is an assembly project. So here's how it works. The first thing that happens is all the peripherals are initialized, which includes the ADC, UStart, and timer 1. And I'm purposely glossing over this part because it's not extremely important in the context of this project. So in assembly language, in order to send any information over the serial monitor, it has to be sent as a stream of ASCII characters. So ASCII stands for the American Standard Code for Information Interchange. Basically just a mapping of values to characters. So then the question becomes, in assembly language, how do we convert a binary number into its components or into its several decimal characters? And so the answer to that, or at least one answer, which is what we used in this project, is to convert the number to BCD, or binary coded decimal first. And so to do this, we arrive at what's the good part of the project, the shift and add 3 algorithm, otherwise known as Dabble. So the shift and add 3 algorithm is exactly what it sounds like. Everything is shifted left, and you add 3 to a nibble when it's 5 or more. So very quickly, let's run through a sample conversion. So let's say we start with the number 151, which is 10010111 in binary. So this is an 8-bit binary value, and an 8-bit value can have a maximum of 255, which means we'll need 3 BCD digits. So the first thing you do in the shift and add 3 algorithm is you set up what's called a BCD scratch space. So the input is 10010111, and then each BCD digit will be 1 nibble or 4 bytes long. So the first one, it overflows into the next scratch space. And the important thing to note is that the numbers that roll in on the right are zeros. So then we examine every nibble. Are any of them greater than 5? This one's 1, the others are 0. No, so we shift again. Again, no nibbles are greater than or equal to 5, so we shift again. Shift again. Okay, so now this nibble is equal to 9, which is greater than 5. So what we do is we add 3 to the nibble. So 9 plus 3 is 12. So these are still going to be zeros. But this is now going to be a 12. So that's going to be a 8 plus 4. Okay, so after that lengthy conversion, we can now see that all the 1s have been moved to the left, and we started with a 1 in the least significant bit, so that means that we're done because we've shifted it 8 times. So now if we read each nibble, we have 1, 1 plus 0 plus 4, 5, another 1. So if we put those together, we have 151, and then if we look, that was our original input, so we did that right. The shift and add 3 algorithm does indeed work. So while that was relatively easy to implement with a pen and paper, albeit a little bit tedious, it is slightly more difficult to implement in assembly language. So let's get into how that works. So the first thing that happens is that a register called count is initialized with a value equal to 16 because we have a 16-bit value. So the first line is load immediate, and then we're putting the number of bytes, which is a predefined, into the register called count. So count, comma, bytes. Next, we just want to clear all our registers. So that was the setup. So now we have a label called next, and this is where the program counter is going to jump to every iteration. So on each iteration, the first thing we're going to do is we're going to shift left. So to do that, what we do is we shift each, going back to our pen and paper, each byte is a register. So since we have to get each register to overflow into each other, we can use the rotate function. And the rotate function essentially takes, rather than bringing a 0 in from the right, it takes whatever was in the carry. So if we do a logical shift left of bin 0, which is the low byte of the input, we're going to shift everything left, and then the leftmost bit is going to overflow into the carry. So now if we do a rotate left of bin 1, we're going to take in, on the right side, we're going to take in the value of the carry bit, which was the high bit of bin 0. So then if we repeat the rotate left of bin 1, and we repeat that on BCD 01, BCD 02, and finally BCD 4, we've essentially shifted our entire scratch space and inputs left 1. If it is the last count, then the count will equal 1, so we're going to branch if equal to the end. If not, it's just going to continue. So now what we're going to do is we're going to check each nibble to see its value. So basically the way that works is we move the value in any one of these. So I'm just going to show one example, but we're going to take bin 0 and we're going to put it in the utility register. So we're going to do, so that's going to move bin 0 into the utility register. And then we can manipulate the utility register however we want without affecting the initial value. And so we're going to AND it with a mask. Let's say we're doing the low nibble, we're going to do AND immediate, and we're going to AND the utility with the low, with all ones on the low side. So hex 0f. So it's going to wipe out the upper nibble, and it's going to guarantee that the lower nibble remains the same. Finally, we're going to compare that. We're going to compare with 5. So we're going to do utility compared to the number 5. And then if it's less than 5, or if it's not greater than or equal to 5, so we're going to go branch if lower than to skip low byte. And then the next line is just going to be subtract immediate, and we're going to just subtract -3 from utility because there's no add immediate instruction, but by subtracting a negative, we're effectively adding a positive. Essentially, that's just going to loop through 16 times, and we end up with the same results as what we did here, and that is how the code works. Thank you so much for watching. I hope you enjoyed this video.